Yeah.
Okay, so it's 2:02 now. Let's get started. Hi there, welcome to Ask Seminar Series. This is John, Seminar Coordinator. I'll be moderating this seminar with Kathy Medley, our Communication Manager. And just so you know, then this seminar is being recorded, and we will publish the recording on our YouTube channel. And after the presentation, we'll have a Q&A session. We encourage you to ask any questions. And before the speaker gets started, I will hand this over to our Associate Director, Prof. to introduce the speaker. So, Prof, please go ahead.
Yeah, thanks. Yeah, it's my pleasure to introduce Professor Amanda Lynch, who's a distinguished professor at the Department of Earth and Environmental and Planetary Sciences at Brown University. She's a world leader on Arctic climate and research. She's got her PhD from University of Melbourne, created the first Arctic regional climate system model, and has also got a bunch of other honors and awards. Has also wrote some books on the topic and authored over 100 papers. So without further introduction, I just turn it over to her, and I look forward to what looks like to be a really interesting talk.
Great. Thanks very much, Ralph. And I really appreciate the opportunity to speak to everyone today.
Yeah.
So I will share my screen, and hopefully this will work okay. So assuming everyone can see that, someone will yell if they can't. What I'd like to talk about today is some of the results that we're seeing from a project that I've been leading called Converging Pressures in Arctic Development. And we've been generating some pretty interesting ideas in this process and working out how to work across disciplines. And so I wanted to report on some of the key conclusions that we've been developing here. And I just wanted to note, because the question was asked before this session began, this is not an AI generated image. It actually predates that. It's from an advertisement for icebreakers. So this work on converging pressures in Arctic development was really motivated from the understanding that climate change is amplified in its impacts, in its intensity, its pace in the Arctic compared to other parts of the world for some well understood and perhaps less well understood reasons. So this amplification is apparent in many aspects of the Arctic physical systems, including particularly the cryosphere. And of course, because Arctic development over the past centuries have depended upon the predictable behavior of that cryosphere, these rapid changes are having impacts on human activities in the Arctic and indeed aspirations for the future. And this idea of Arctic amplification has led over the past probably decade or so to this idea of the race to the north, that these projected cryospheric impacts are going to unleash an opportunity for economic development and strategic exploitation. This is one of the maps that was developed thinking about this, particularly associated with mining, hydrocarbon exploitation, and military development. And of course, these expectations for opportunity has led to an increasing intensification of claims to territory in the Arctic across many different domains, from shipping lanes to deep seabed mining to indeed self-determination in the case of Greenland. And so what I'm going to do today is talk about a few very specific areas that we've been looking at across this project. I'll spend most of my time talking about sea ice retreat, but also talk about a little bit about snow and permafrost as well. And the motivating idea of this project has been to think about the information that we can develop as natural system scientists, particularly about the climate system and changes in the cryosphere, but also other elements of the natural system. And in what ways can this information be utilised to support better decision-making in the face of rapid change and high uncertainty? And so that's what I'll be focusing on very much, is what knowledge is useful that we can generate on the science. So the first example I want to give is based on our studies of sea ice and maritime operations. So you can see here on the right the various routes across the Arctic, which typically in the past have skirted the coastline of Russia or the coastline of the US and Canada. So those are the Northeast Passage and the Northwest Passage. And then this postulated transpolar sea route that would go right over the top if the ice conditions and other enabling technologies such as communications and satellite coverage and emergency management and those kinds of important areas, if those were available. And so in thinking about sea ice futures for navigation, the obvious place to start is to think about CMIP scenarios. These are a range of CMIP scenarios that we used based on the Sea Ice MIP or Sea Ice Model into Comparison project, did an analysis of the climate model scenarios that were doing the best job of present day Arctic ice. And we took that subset and projected them into the future to develop a set of scenarios. And then there's readily available commercial software. It's called Polaris, which allows you to use the ice characteristics from those scenarios to project navigability on any given day. And then from that, you can calculate the length of the shipping season, the length of time that ice is reliably clear enough to allow passage. And you can select for different classes of polar class vessels. That's their level of ice strengthening. And so these are actually open water vessels, but we did this for all of the polar classes. And we calculated the length of the shipping season and the year the 90-day season was achieved, because in our discussions with operations managers at shipping companies, a 90-day season was required for economic viability of this route. The reason that this is interesting is because the Arctic route is shorter than the Suez Canal, even when you allow for the fact that ships have to travel at a slower speed through the Arctic, and they tend to be somewhat smaller ships than the Suez Canal. So those are the negatives, but the positives are it's still shorter in time as well as in distance, even allowing for that, particularly because there's been a global go slow on shipping in order to reduce emissions. There is also the absence of bottlenecks. The Suez Canal represents a bottleneck. There are also risks associated with piracy, but then you have, a lot of other elements as well associated with insurance, associated with tolls and tariffs, and it's quite complex. And I'm not going to go into all of that. We're just going to look at the use of the climate information. So can we use this to evaluate the cost of using the Suez Canal if in fact the Arctic route had been planned, but the season could not be provided at sufficient length. And so we work with some economists on developing the ratio of costs using the Suez Canal with its longer distance and risks associated with the bottleneck compared to the cost of using the Arctic route. And what we found was that both interannual variability and the high model uncertainty cost. So what you can see on this graph is as we move from the ratio of supplied to needed season length, that 1 is 90 days. To the right of that is that the Arctic is providing as much shipping time as is needed. And to the left of that is that the ice is starting to shut things down. Now, if we use the ensemble mean and project the costs associated with that and consider the risk of not realizing that needed season length, the ensemble mean underestimates the cost by a significant amount, and that's the green dashed line. Whereas if you estimate the costs of every one of those ensemble members and take the mean cost curve of that, you get the blue dashed line, which is right in the middle, of course, of the cloud of realizations. And so using the multi-model ensemble mean, which in other knowledge domains would be considered to be the best available information projecting forward, underestimates the variance that operators are seeking to assume. And so it's a poor substitute for having the whole ensemble. But of course, the other issue is that the interannual variability weighs more than the model uncertainty when we're right at that needed season length. That's where the cost difference between the realized and the projected assessment is at its maximum. And so what this tells us is that we need to account for interannual variability and model uncertainty, and we can't average those out at any point until the end of the assessment. And then there's the question of geopolitics. So in the United Nations Convention of the Law of the Sea, which is the convention that governs all of the oceans, including the Arctic Ocean, there is an article, number 234, which covers the presence of ice. And this is an excerpt from that article where it notes that coastal states have the right to adopt and enforce laws and regulations where the presence of ice for most of the year creates obstructions or hazards to navigation. And of course, as a scientist, the presence of ice, how much ice, what kind of ice, how thick is it, what is its concentration, and then for most of the year, exactly how much of the year is this talking about? And this is a kind of something of a productive ambiguity in the context of law, but it leads us to think about what we can say on the basis of climate. Now, Article 234 is intended as a specialist law for coastal state authority to protect the environment. It was really about protecting the environment, ensuring that pollution didn't occur, and when it did, that the states could regulate cleanup of that, of any kind of toxic spill. But Russia has invoked this article as a law to allow it to extend enforcement of its jurisdiction into the Northern Sea route. And they do this in a kind of it's a little bit of a hall of mirrors where they simultaneously say that the Northern Sea route is internal waters, but then they also say that it is navigable waters according to Article 234, and so they have extra jurisdiction anyway. So they're kind of having their cake and eating it too. And so one of the things that we were then able to do is to, using those scenarios and the model of navigability, we could consider what the length of the shipping season would be for any of the future climate scenarios at that time, and consider what is the probability that you could have a shipping season of sufficient length that was completely outside of Russian territorial waters. And so that was the question that we asked of our models, and we were able to develop this assessment of navigation probability using the IPCC measures for unlikely, as likely as not likely, and so forth, to determine when it would be possible to routinely navigate outside of Russian territorial waters. Now, the rate of change depends on the scenario in the out years, but certainly, in the coming several decades, while it's relatively unlikely, on some of our higher trajectories, it's going to become much more routine. And then this lets us start to consider the types of impacts of this, not just on commercial shipping, but on, for example, freedom of navigation exercises that are done by other states in the Arctic. However, this process is still not sufficient for the current situation, where navigation, in fact, has to occur largely within those coastal waters, because those coastal waters primarily take advantage of some fairly sheltered straits. And that's true both on the Northern Sea route and on the Northwest Passage. And by using climate scenarios, we're actually making some assumptions about what the ice is doing in those straits. And again, this is something that's fairly routinely done operationally, because most of the users of this model don't have eyes on what the CMIP6 grid actually looks like. They typically look at a 25 by 25 net, which is an interpolation of this grid. And standard interpolation methods tend to underestimate the ice in straits. And so you will preferentially get viable routes being routed through those straits in these scenarios. And so one of the things that we did was to use a super resolution machine learning approach. In this case, it was a generative adversarial network that we call iScan, to be trained on high resolution data, which you can see in the center here. We trained it on high resolution ERA data, reanalysis data, and we sought to use the climate model resolution on the left-hand side to generate a high resolution picture, which you see on the right-hand side, that's using our iScan super resolution method. And as you can see, it does a much better job of replicating the ice, in fact, some quite high concentration ice in the strait, which would then block passage in ways that an interpolation may not necessarily capture. And so these are some of the kind of many different ways that we're using to think about the kinds of knowledge that we can start to bring to bear, either on questions of commercial planning, questions of law, questions of strategic operations, and that the kinds of questions that we need to ask of our models tend to be quite different from the ways in which we might address the performance of the models and how we think about what they're telling us if we're just interested in the scientific insight. And so another example of this is some work that we did looking at snow futures. And we wanted to look at this in particular for its impact on reindeer. So across the Arctic, reindeer are used for subsistence purposes. You can see here on the left, we have a photograph from Sami country, which is up in northern Scandinavia, Finland, Norway, Sweden, and into the Russian Republic. On the right-hand side, you have Sakha, the Sakha Republic, which is in far eastern Russia. And these are both areas where reindeer are a critical part of the local economy. But reindeer are sensitive to very deep snow, and they're also sensitive to layers of solid ice in the snow, which can form when the snow melts and refreezes, or when you have rain on snow events. Sometimes too, you can get very solid, firm, dry layers that just occur due to compaction over time. And so a long duration of those kinds of problematic characteristics can lead to increased reindeer mortality. And in our work, particularly with some Sakha community members and large animal biologists, is that if you have 5 straight days of these kinds of problematic characteristics, you can have a significant die-off of the reindeer herd at that point. And so what we wanted to do was to see if we could say something about snow futures for these kinds of questions. And so to do that, we implemented a snowpack model, which was actually used primarily for avalanche forecasting in mountains. It was originally developed in Switzerland. It had been used in an isolated way at single meteorological stations to look at the impact of snow characteristics in other domains. And so that gave us some confidence to move forward and consider how this might impact the reindeer. So again, we used multi-model ensembles, and we did a total of almost 12,000 snow year simulations across locations and climate scenarios to try and get a sense of how snow was going to develop in ways that would be good or bad for reindeer. And this shows you an example of a particular day. This was a simulation from March 26, 1991. And you can see going on the left-hand panel, the growth of the snowpack through the season starting in late 1990 the slice in March 26th is right in the middle of that snow season. And those red layers are melt freeze crust, which are too hard for reindeer to break into. So we did all of these simulations, and then we calculated the frequency of days that were the snow was too deep, even if it was soft, for reindeer to break through. And again, we got that measurement from the Sakha large animal biologists. It's about knee deep. It starts to be a problem for them. And then also these persistence of these solid ice crust areas. And we looked at the frequency of those kinds of problematic situations that persisted for 5 days or longer. And what we found is that, of course, the thing we all know, climate is warming, the snow season will be shorter and warmer. And so that's, that's not useful for decision making. What we found was that deep snow events become less frequent in Sapmi, in the Sami land of northern Scandinavia, but more frequent in the Sakha Republic as we move forward in time through to the late part of this century. And that layers that are too firm or icy for reindeer to break through become more frequent in both locations through that time period. So we get more of these melt freeze events or rain on snow events. And so there's an increase in ice incidents. This is one example. It's a small increase, and you might say 1 or 2 incidences a year is not too many, but that one incident is 5 days of reindeer being unable to forage and increased reindeer mortality. And so even one incident is significant for that community. And what we're seeing is an increase over time. Now, what's useful about this is that it doesn't just deliver bad news, but it allows us to look at policy settings that might be useful for this. And one of the things that we were able to talk about with our collaborators is that in icy conditions, reindeer tend to seek forage preferentially in old growth forest. They don't like the kind of tree plantations that you have across Finland, but in old growth forest, they can go into those areas and they forage on the vertical branches and trunks for lichen, and they're able to survive that 5-day period. And so what that suggests then is a policy setting associated with creating corridors for reindeer to be able to access these patches of old growth forest in these periods that are icy or too deep for them to access their forage. And so that was the work that we did on snow. Another part of this project we were looking at was permafrost, and in particular thinking about the bearing capacity of the permafrost under the road network. And of course, in all season situations, you want that road network to be functioning throughout summer, even when there is some increase in active layer depth, that the bearing capacity is maintained. But in winter, there are other options. And so in winter, you can have travel over ice roads, which are over water bodies, if there is sufficient freezing to have sufficient bearing capacity over water bodies, and over the snowpack, again, if it's sufficiently compacted, it can provide additional options. And so we developed a model to look at the evolution of this capacity throughout these networks over time. And so what we found in this case is that travel costs increase in all climate scenarios for most locations associated with that very large increase in active layer depth, in the increase in discontinuous permafrost, the loss of the permanently frozen ground. And so as you can see, for low emissions and high emissions scenarios, there are large and significant changes in accessibility, particularly in parts of Finland, also in Russia and Canada. There are a few places that actually benefit from this warming, and some of that's associated also with rivers and other options. But what we found that I think was most critical was that 40 settlements under the high emission scenarios are projected to become inaccessible for part of the year by any of these means by mid-century. And so this kind of forward projections of terrestrial accessibility is important in terms of planning for developing infrastructure for alternative access arrangements for these communities. And so now that's what I want to talk about a little bit more, is thinking about the future and how we can start to get a handle on what the options are there. And so there are, of course, many possible overlapping future pathways. We can see that rapid and intense climate change is manifest in many of these areas. But of course, the Arctic is still dark, stormy, remote, has poor communications coverage, has poor satellite coverage, doesn't have enough experienced operators, particularly pilots in the maritime situation. And so it's an opportunity for some, but it's a significant challenge for others. And so working with a large cohort of decision makers, both in industry and in government, from community level up to national level, we developed a set of scenarios of possible future pathways. So this ranged from resilient communities, what might be an ideal situation where there's investment in sustainability, education, employment, there's increased autonomy and self-determination. There were ideas about a Silicon Valley North, with this idea of growing technology hubs or infrastructure such as server farms in cooler areas. And then there were problems such as going for broke, so a heavy increase in extractive industry, so doubling down on the opportunity side of this, that hydrocarbon exploitation, land-based mines and deep seabed mining would all be exploited. So we looked at all of these possible future pathways and interrogated decision makers about the ways they were thinking about what these possibilities might be and what that meant for their decisions. And of course, very clearly, future pathways depend on existing capacities. And so this is one of the other things that we've been working on mapping in this project, is where all these capacities lie. And this is a kind of a short list of some of the things we looked at. So we certainly looked at things like transportation networks, infrastructure, emergency services, telecommunications, but we also looked at other elements. So, for example, the contributions of Indigenous and traditional cultures to decision-making and how they could inform positive adaptation. We looked at human health and well-being and how that might be supported under different scenarios and what that needed in terms of, for example, healthcare networks. And then, of course, there's the capacity of the people of the Arctic as well, in terms of their professional, scientific and technical capabilities to realise these aspirations. And so this has been a mapping process that we've been going through over the past few years with some support of RAND, along with our partner universities in the project. And this mapping is really intended to be a first cut, to be ground truthed by ourselves and other investigators. We're at the moment, we're developing some ground truthing activities in northern Norway, but ultimately this database will be made available to the Arctic research community for their own use and interrogation and improvement. So one of the things we developed with these decision makers was scenarios, development scenarios. And from this, we came up with this view based on the many Arctics idea, the fact that, you know, if you've been to one place in the Arctic, you've been to one place in the Arctic, that all of these places are very different. But we were able to usefully group them roughly into 4 zones, although I think that this was all done before the invasion of Ukraine, and so we might kind of consider the Bering-Beaufort area a little bit differently now than we did when we initially came up with this grouping of 4, and we might end up indeed splitting it further than just 4. But it's a good first cut, and like climate models, all development scenarios are wrong, but some are useful. So we asked them to do an assessment of the current status and then consider possible departures. So, for example, for the Barents area, you know, northern Scandinavia, and indeed into Russia, there was a sense at that time before the invasion that there was pushing towards resilient communities, certainly pushing very hard on this idea of a vacation destination. Sorry about spelling error. But that there was a thought that what they really wanted to think about was Silicon Valley North. And that was something that a lot of the communities there were thinking very strongly about. But even at that time, there were concerns about geostrategic spill, that what would happen if there was an issue that led to a kind of a bifurcation between Scandinavian futures and Western Russian futures. And indeed, that departure is exactly what has come to pass. And so, you know, if we think about the Bering-Beaufort as another area, that was very much focused on fisheries primarily, a certain amount of mining and hydrocarbon development, but a strong sense that that fisheries was the way that those communities wanted to be going in. There was a sense that perhaps there would be an opportunity for a departure into becoming more of a vacation destination, but there was also a concern that this going for broke, this mining and hydrocarbon exploitation future would actually be the direction that the scenario went, and that might lead to failure. And so you can see that, you know, these narratives can create useful ideas about pathways going forward that we can then use our climate scenarios to help to constrain the range of possibility and also identify the risks. And so with that, I'd like to thank all of my collaborators. As you can imagine, this is a project that has many different people with different expertise, but the results I've cited here come from my collaborators, Shueika Lee, Maria Luisa Rocha Santos da Silva, Charles Norke, Kat Landers, Dima Streletsky, Emma Perkins, and Michael Goldstein. And I'd also like to refer you to the website if you're interested in more information. And with that, I will open for questions. Thank you.
Thank you, Professor Lynch. So if you have any questions, you can raise your hand or just let me know in the chat. Or you can also type the question in the chat if you don't have a microphone. Questions? Surely one of you has a question.
Have you considered what the melting permafrost might do from a greenhouse gas perspective, or is that a little bit beyond your focus?
Yeah, so we that is beyond our focus. We are not looking at the biophysical ramifications of the changes. We're really looking at the social ramifications and even within the social ramifications, very specifically infrastructure, economy, and geopolitics. And so those are the areas. So we're essentially saying, you know, if this is what you're experiencing and this is what you're hoping for, these are your aspirations, what are the risks that that the climate, the evolving climate presents to those aspirations? One of the actually, and to that end, particularly thinking about thawing permafrost, we haven't really thought about, you know, for want of a better words, tipping points or accelerations of change. And that's, you know, it's one of those things where it's high impact, but low predictability. And so we've not concerned ourselves with that so much. And I guess the way we reconcile ourselves to that is by talking mostly, when we're talking with our civil society partners, we talk to them mostly about what they're planning between now and 2050 to try and constrain it.
Thank you. We also have a question. Actually, now we have a couple questions in the chat. So the first one is, are you participating in WMO's PCAPs? This kind of services and decisions consideration is squarely in the project scope.
Yeah. So I'm kind of, I have eyes on PCAPs because I have other roles at WMO. And so what our hope is with PCAPs, and I've spoken to a few people who have been involved in the, you know, in the steering committee of that, is that when we release the database, which we're hoping to do in the coming year, that one of the things we'll be flagging is whether that is a community that would help us improve it. Because I definitely see all of this is, because we're trying to span the whole Arctic, it's going to necessarily be the first cut of a lot of things. And so what I've flagged with the PCAPs folks is that this might be a resource that they could use to improve upon, particularly in the emergency management area, which is an area I have a student who's particularly decided to kind of go down that route and look at that. And that's very much, I think, where PCAPs will be particularly useful.
Yeah, that question asker noted that they are also in PCAPs.
Oh,
so
I haven't spoken to you about it yet, Bob.
You have another question. So for the sea ice in the straits climate predictions, do the models, machine learning or otherwise, predict the types of ice, multi-year, first year sea ice, glacial ice, etc., that are expected? Some have greater impacts on shipping than others.
Yeah, so most of the models have within the actual sea ice model of the climate model, they typically have within a grid cell, they have an ice distribution. And so you'll have different ice categories within a grid cell, and that those will grow and melt and move around over time. And so kind of by default, then yeah, they're dealing with multi-year ice, first-year ice, and so the models that we're using, they the commercial models consider ice concentration primarily. So what they care about is how much open water there is, because that's, you know, where the polar code comes in. But then their ice thickness instrument in the polar code is kind of a blunt instrument. And so we actually have more detail than they would typically use when we're doing that.
Thank you. We have one other chat question. She asks, you may have discussed this in detail already. if you have interacted with stakeholders in the shipping industry, how receptive did they seem to rerouting through the Arctic / estimates on the reduction in shipping costs versus Suez?
They were very receptive. A couple of the corporations, operations managers that we worked with, the way they put it was, we're not scared of icebergs. We're scared of icebergs of Russian bureaucracy. So that was what was stopping them, was the fact that the viable routes right now require them to adhere to Russian regulations and Russian tolls. I mean, the Russians basically treat that route as a toll road, and they require you to have icebreaker escort supplied by them. They require a pilot supplied by them. There are restrictions on the flag, particularly at the moment. Of course, all bets are off. But and so they were receptive to doing it. But they wanted to do it outside of Russian control, which was part of what led us to do that, scenario development of, well, how soon is that even likely that you could reasonably do that? I mean, the fact is, Russian ships use that route 12 months a year with no problems at all, because they have ice strengthened vessels, although they're even doing it with non-ice strengthened vessels now, but it's quite routine for them. So a lot of it is to do with it's actually to do with the paperwork that they have to do, and that's and the costs associated with that. But yeah, they're very keen on it, because there are regulations coming down for reducing emissions, and that's an issue. And getting around the bottleneck that is Suez, both based on accidents but also based on piracy.
Interesting. Okay, so here's another question. I may not have read enough of the future scenario slide, but what did you mean by carbon sink as a departure from the current use expectations? What allows the Arctic to be a carbon sink?
So this was one of the ideas that was postulated to us, particularly in Scandinavia, was they were very interested in expansion of forests. And so they wanted to explore that as a possibility that they could do that. The other thing they were talking about were more associated with geoengineering type situations, where you might do carbon fertilization of the ocean. And so they were talking on both of those sides, was what we were getting out of the operations people. So, and we weren't filtering that for whether it was realistic or not. We were looking to see what their scenarios were.
Thank you. So that is the end of my queue. Does anyone else have any last minute questions they want to ask Professor Lynch while we still have her attention? Okay, well, thank you everyone so much for attending, and thank you to Professor Lynch for giving us this great talk. A recording of this talk will be available probably in about a week, maybe by the end of this week if I'm lucky. And we will continue our seminar series next week, but I believe we are doing it on, we're doing it on Tuesday next week because Monday is a federal holiday. So thank you everybody. Have a great day.
Yeah, thanks, Amanda. Very interesting work.
Thank you. Thanks very much.
You're getting a lot of thank yous in the chat too, Amanda. Just want to make sure you see that.
Thanks a lot. Okay,
Cool.
cheers.
Have a good one.